These are the motors that power the modern world. But the problem with these is that these are heavy, bulky, and waste a lot of energy. For most applications, that's fine. But there are places where that is simply not acceptable. In space vehicles, one extra kilogram costs thousands of dollars and can cost the mission. In a drone or an aerospace actuator, one extra gram of motor is one less gram of payload, or 1 minute less in the air. In a robotic joint, every watt wasted is heat, and heat at that scale is failure. In an EV, the motor size is the difference between fitting in the wheel hub or redesigning the entire chassis. So, meet the Yokeless Axial Flux Motor. Instead of a cylinder, it's a disc. Ultra thin, lightweight, and fundamentally rethought. Conventional motors carry a heavy iron ring, the stator yoke, that exists purely to guide magnetic flux. We eliminated it entirely. The result, up to 3 times more torque for the same weight in a form factor that fits where no conventional motor can. Every dimension of this motor material was designed from first principles and validated through electromagnetic FPA simulation, ensuring real-world performance before a single part was machined. This design earned industry validation and led to commissioning of Pakistan's first YAFM prototype. However, a powerful motor still needs a brain, and this motor cannot be driven by any off-the-shelf controller, so we built one, a custom field-oriented control architecture that gives us precise command over speed, torque, direction, and exact angular position. This motor reaches the target speed and locks to the target position in just a blink of an eye. Then we took this entire algorithm, wrote it in embedded C, and deployed it on a RISC-V open source processor, proving this system can be built at scale. So, motor designed, control algorithm built, deployed and verified on silicon, end to end. This is what indigenous sovereign next generation engineering looks like.